doing internal loads and beams. And the idea is based on the superposition principle, and that's a pretty common thing when you have small, well, in our case, we're talking about small deformations. But anytime you have small perturbations from some sort of reference position, that's when the superposition principle can come up. So it's such a cool name for such a simple thing. And the idea is just that for our case, and by that I mean, I guess the only thing that matters in this case for us is the fact that the deformations are small. But the stress tensor total is equal to, and this is in a beam, it's equal to the stress tensor due to tension plus the stress tensor due to bending moment plus the stress tensor due to the shear force plus the stress tensor due to the torque. And when I talk about adding these stress tensors, they add the same way that vectors do, just element by element. So for example, if you have stress tensor 5, 0, 2, 0, 1, 0, 2, 0, -3, and you add that to 0, 5, 2, 5, 0, -4, 2, -4, 1. You just add them up element by element. So 5 plus 0 is 5, 0 plus 5 is 5, 2 plus 2 is 4, 5 plus 0 is 5, 1 plus 0 is 1, 0 plus -4 is -4, 2 plus 2 is 4, 0 minus 4 is -4, and then -2. Well, no. So I was just going to say that. I made those two symmetrical, and notice that if the two you're adding are symmetrical, the other one has to come out that way. So you never have to worry about adding stress tensors and they come out as something that can't be a stress tensor. And the reason this works is basically like, I mean, you can imagine if you bend something really sharply, bend it all the way down to a very noticeable angle, and then you applied tension to it, those loading patterns are going to react in some unpredictable way. But if all of these things are very close to their original configuration, because we're talking about very small deformations, then you have to worry about that a lot less. And those things, you get good accuracy by just calculating independently those loads. First think about a bar that's in pure tension, calculate the stress tensor. Now think about a bar that's in pure bending moment, calculate the stress tensor. So that's what we're going to do, add them all together at the end. And the general idea is for each type of stress, the stress tensor will depend on the internal load at the desired point. So all the stuff we just went through for internal loads is going to be the starting point for the stress calculations. All right, well, we're going to start with the easiest case. So stresses due to tension and compression. And we're going to use the coordinate system that we've used in all of our internal loads calculations, where the x-axis is along the length of the beam, the y-axis is up, and the z-axis is out towards us. And at any point in the beam, that has an internal load or an internal tension T, the normal stress in the x direction is equal to T over A, where A is the cross-sectional area at that point. Okay, so this doesn't say anything about where on the cross-section you are, and that's because over the whole cross-section, the stress is the same. So it doesn't matter if you're near the top of the beam or the middle of the beam or whatever. All that matters is the x position. So let's do an example. Let's say we have a beam that when we figure out the external loads, there's a 8,000 Newton force at the left end. At the middle, there's a 2,000 Newton force. And then at the end, there's a 6,000 Newton force. And the cross-sectional area let's say it's constant over the whole thing at 0.001. Yeah, meters squared. So what are the stresses as functions of x? You know, how is the stress in the beam going to change as you go along the length? Well, we're always going to start by calculating the internal loads. So how many cuts do we have to make? Normally we'd have to calculate the external loads, but they're already given. 2 cuts, yep. So the first cut is going to be for x between, I didn't say how long this was. Let's say 0.5 meter each. Okay, so the first cut is from 0 to 0.5. So we'll take some representative cut. We have the 8,000 Newton force at the left end. but we haven't gotten to the 2,000 Newton force yet. So the only other loads are the tension, the shear force, bending moment, all that stuff's going to be zero. All we have is forces along the x-axis here, so I'm just going to write it like this. But if you wanted to go through the full calculation, you could calculate shear force is zero, moment zero, fancy T is zero. And then Newton's second law says negative 8,000, 0 plus T0 is equal to zeros. So we got that T is equal to positive 8,000 for every x value between 0 and 0.5. And that's a positive value, so that means that that whole piece is in tension. And now cut 2 is between 0.5 and 1. So now we have the 8,000 here. And now somewhere else we have the 2,000 going the other way. And the tension. And so Newton's second law says negative 8,000, 0, plus positive 2,000, 0, plus T0 is equal to zeros. And so T is equal to 6,000. So now that we have the internal loads, for any x values between 0 and 0.5, sigma xx is equal to positive 8,000 divided by 0.001. And so that's 8.0 times 10 to the 6 pascals. And if you wanted to give the full stress tensor, that's the XX element. So that's 8.0, 0, 0, zeros everywhere else, if you write it in megapascals. And notice, if you think about what that means, a positive, so a positive tension as an internal load means the thing's in tension. A negative value means compression. And now think about the stress element, and it means the same thing. So we're going to use the sign that we get for the internal loads to calculate that stress, and it works out, the meaning makes sense. I'll write that in a second. And on the other half, for x in the range from 0.5 to 1, the XX stress is positive 6,000 divided by 0.001, and that's 6.0 times 10 to the 6 pascals. And so the stress tensor on that half, for any point on that half, is 6.0, zeros everywhere else. In megapascals. So now what that says is, in this case, if you're trying to figure out where you're concerned about this bar breaking or deforming permanently or something like that, the half that you know, the place that you want to investigate is the left half of this beam. Okay, that's where the stresses are higher, and so that's what you're worried about. If it's good on the left half, then it's good on the right half too. Okay. Well, if the right half had a different cross-sectional area, then, you know, say that the cross-sectional area got smaller on the right half of the beam, then it's possible that even though the internal loads are bigger on the left half, the stresses when you divide by the cross-sectional area would be bigger on the right half. So this is the best indicator of how concerned you are about fracture or whatever. Okay, so I want you to notice one thing. Trust the signs from the internal tension. That's going to be true for every one of these calculations, I think. Maybe not torsion now that I think about it. But I'm going to make a point out of it every time that it's a thing. Okay, so we just, whether it's positive or negative coming from the internal loads, we use that signed value to calculate the stress. Yes? Well, we don't know that it's going to break at all. We just know that, so there are different kinds of kinds of criteria you use for different types of materials to determine whether you think it's going to break. For very brittle materials, we'd mostly just want to calculate the maximum shear stress. We use this value to calculate the maximum shear stress in this environment. And then we go to some table. And for our material, compare to the maximum shear stress you expect for that material. And if our value is higher, then we need to do something, either make the cross-sectional area bigger or reduce the load somehow. For materials that can stretch more before they break, more ductile materials, metals, we would want to calculate the strain energy, which is a combination of the stress and the strain. We're not going to talk about those kind of things, but it's not like the calculations are hard. But it's more just not really a part of this class because the criteria you use are so different for different types of materials. But anyways, so we would take our loads, calculate our strains, figure out whether we think under those loads this thing is going to break or not. If it looks like it's safe, then we're good. If our strain energy value or our maximum shear stress or whatever criteria is bigger than the maximum that material can sustain, we have to do something about it. But so a lot of times we're just going to be looking, we're going to want to just identify the points where we're most concerned about the material, where the loads are the biggest, the stresses are the biggest. And then if it's fine there, then we don't care about it at all. Okay, so that was the easy one. I think I'm going to be sick forever now. It's been like since Sunday. Yeah, I'm used to it. It's all right. That stress is due to tension compression. That's the easiest one. So now we're going on to the next one, and I'm sort of like going in order of complexity of thinking about it in a way. So the next one is stresses due to bending moment. And this is the first one where we really have to worry about whether our beam meets the criteria. There are restrictions on what kind of beams we can do this analysis for. So careful. There are restrictions on allowable beams in this case. Okay, so here are the beam requirements for stress due to bending. Okay, the first one is the beam needs to be straight or nearly straight. What does nearly straight mean? It just means that the more curved it is, the more inaccurate your answer is. So if it's a gentle curve where the angle doesn't change too much over the length of the thing, then you'll get pretty good results this way. If it's a circular shape, you'll get bad results. But I don't really have any values to judge this by. So for all of these, I'll just give examples of what I'm talking about. So we can do beams like this. Well, you know what a straight beam looks like. But we can't use this to calculate stresses in something like that. Okay. There are ways to do that, but you have to modify this approach a little bit. Second, the beam needs to be prismatic or nearly prismatic. So again, beams like this are fine. The cross sections don't change as a function of x. So something like this, or where that angle isn't too big between the walls, or even if it's slowly changing from like a square shape to a circular shape or something over x, you can use this approach. But if you have a violent change, you know what I mean, of a very drastic change as x changes in the cross section, these won't give you good results. And then the third and the last one is that the cross section has to be symmetric about the y-axis. Okay, so shape like this, a cross-sectional shape like this, and our coordinate system would have, the way I'm looking at the cross-section, the x-axis would be out towards us, the y-axis would be up, and the z-axis would be this way. We can calculate the stresses in a shape like this. We can't calculate the stresses in a shape like this. I'm drawing the same shape. But now it's tilted the other way. And um, on the second or third time you think about this, you think to yourself, well, why don't we just change the coordinate system and then it's fine? Well, the key thing is the coordinate system is um, chosen once you know the axis that you're bending around. It's not really the y-axis that defines what I'm talking about. It's that the z-axis is the axis of the bend. Okay, so and so it really depends on the loading environment, not on how you choose your coordinate system. Okay, so what am I talking about? Well, you know, when we do rotational Newton's second law, there are only two components that we ever use. One is x, and that's if it's being torqued, okay? And then one is z, and that's if it's being bent by vertical forces, okay? And so here we're talking about the case where this beam is being bent by vertical forces, okay? And so if it's not a problem that this, like you could have a beam like this as long as you just got lucky and all the forces that you were dealing with were in this plane. Then you just redo your coordinate system and you're fine. But the issue is that if this is the cross section of a beam coming out this way and you're applying your forces like this approach won't work. Any questions about that? You know what I'm talking about? Okay, so now how are the stresses due to bending developed? How do they come about? Say. Due to bending. Okay, so let's say we start with a straight beam. Let me draw it a little thicker than that. And then I'm going to draw a really drastic bend, but that's not realistic for the kind of loads we can calculate, but just to get an idea. And that's what you get by applying a couple there and an equal and opposite couple there. And somewhere in the middle here, there is a line where the length of that line, the length of that dotted red line before the deformation is the same as the length during the deformation. So that red line stays the same length under deformation. That line is called the neutral axis. And the neutral axis obviously should be an axis, but it's not, it's a plane. Okay, so there's a lot of confusing things here, and that's only one of many. It's really a plane. Or a surface, I suppose, when you deform it. whichever coordinate, whichever plane you're looking at this problem is, it's an axis. It's an axis like that. And if you look at the cross section, it's an axis going horizontally across the cross section. Yeah, it goes all the way through the cross section. It is what? So what we're looking at here is x. Yeah, we're looking at it in the xy plane, and it's an axis. And if you look at it in the xz plane, it's also an axis. And those two define a plane before the deformation and a curved surface after the deformation. I don't know. You know, because of the small deformations, it deforms into like a U shape. But I think you might be right in sort of having this guess that it gets more complicated as that deformation gets bigger. But so it's like you can just think of it as for our small deformations, you can just think of it as what happens when you curve an aluminum sheet, it's a U from this side, and at every point in the cross section, it's just a line looking at the cross sections. Okay, so if that line stays the same length under deformation, okay, here's a quiz about track. If you want to run a 400-meter race against someone, and one of you is in the inside lane and one of you is in the outside lane, and you're both starting from the same starting line, which lane would you rather be in? Which one's shorter? Inside. So all of the points on this side of the neutral axis are in compression because they're shortened. And all of the lines on this side of the neutral axis are in tension. Okay, so there are a few things I want to say about this. The first one is that stress tensor due to the bending moment only has, so if you think about it that way, if you think about like individual fibers that go this way, okay? And when we deform this material, those individual fibers that are above the neutral axis in this case get shorter, and the ones below the neutral axis get longer. What element of stress? It's an elongation, so we know it's going to be a normal stress. What element of the stress tensor is going to have those non-zero values? Can you even understand what I'm trying to ask? Okay, so imagine a fiber that runs this way, and it starts out above the neutral axis, okay? And after you bend it, you've made that fiber shorter, okay? So you've compressed it. It's a normal stress in compression, so it's going to be negative. What element of that stress tensor is going to have that negative value? Nope, that would be the fibers going this way. So it's XX, yeah. So again, this is only X normal stresses. No. Nope. This is like the view that we take to calculate the external loads and stuff. You know what I mean? So The x-axis is like this, the y-axis is up, z is out towards us. So this only has non-zero XX normal stress. Okay, all we're doing, it might seem a little weird that this is the case with bending, but all we're doing is stretching some fibers and compressing some fibers. And those are all just X normal stress. Second, sigma XX is equal to 0 somewhere in the middle. And that's on the neutral axis. And the neutral axis is really a plane. Third, sigma XX is negative if you move toward the center of curvature. Center of curvature, you can think of that as like the center of a circle. So in the example that I drew here, the center of curvature is that way. Okay, so if you start at the neutral axis and move toward the center of curvature, all the stress values are negative. Okay, those are the fibers that are getting shortened. By fibers, I'm not really talking about actual physical fibers. You know, I'm just sort of trying to picture kind of like a mathematical shape. And then that means that it's positive as we move away from the center of curvature. So there's one big fact that I want you to notice before we go into doing these calculations. On a single cross section, sigma XX was constant for tension, you know, tension and compression. So choose a single cross section, look at any 2 points you want on that cross section. Those values are the same when we're talking about tension compression. Now that we're talking about bending moment, that's not true anymore. If you go above the neutral axis, you get stresses values that are one thing. If you go below the neutral axis, you get stress values that are something else. So that's not true for bending. Sigma XX varies based on points location relative to the neutral axis. That's probably not the best way to say that, but sigma XX varies based on the points location compared to the neutral axis. They're not the same, right? Okay, so before we can do these calculations, we're going to see that the sigma xx due to the bending moment is equal to the bending moment at that desired cross section times y over this value I, and there's going to be a negative sign just to make the signs work out. And so to use this equation, we need two mathematical definitions. The first one is the neutral axis. We know that that is where under the deformation the length of fibers stays constant. And then the second one is that that value I. It's a moment of inertia. In every way, it looks like the mass moment of inertia we use in dynamics, but it's not the same thing. It's calculated very similarly. There's still a parallel axis theorem, but this is the area moment of inertia. And you can think of it as, so this is the value I. And you can think of this as the cross-sectional shape, the cross-section's resistance to bending deformation. Okay, so think of a sheet of paper, okay, and think of this as the beam. That's a side view of the beam. So the x-axis is going this way, y is up, z is out towards you. Okay. And now let's, and so the cross section of this beam is the sharp part of the paper, okay? And think about it in two ways. Okay, so gravity is trying to bend this, right? The weight of this paper, it's not a very big force, but it's applying a bending moment that's trying to bend this over. If I hold it like this, something about the fact that the paper is a lot taller than it is wide keeps the weight from bending it, right? If I apply the same bending moment to it, because it still weighs the same thing, and orient it like this, that bending moment causes a big deformation, okay? So this has a big area moment of inertia. The cross section oriented this way has a big area moment of inertia. It's very resistant to bending. If I do it like this, it has a very small area moment of inertia. It's really easy to bend. And so that's what that calculation is going to get at. Yep. Yeah, it's basically, so the reason they have the same name is because a moment is a mathematical integral thing, and you calculate them pretty similarly. Where we used mass, we integrated with respect to m in dynamics. Now we're going to integrate with respect to area. Otherwise, it's pretty similar. Any other questions? Okay. Well, I mean, what's better than getting to the weekend and we haven't gotten far enough to do any problems? All right. Have a good weekend.